short for 30 minutes into the class, but they didn't do that today.
Okay, so we'll continue, we'll press on. So you know what this is already. Well, tell me what this is. Rho over epsilon. Okay. We can now write this under the context of dielectrics as rho free plus rho bound over epsilon naught. Of course, rho bound is given by what? It's defined by the expression negative divergence of P, the polarization vector. So, if I take the divergence of epsilon naught times E, so I'm multiplying both sides by epsilon naught here, I would get, on this side, I would get rho F minus divergence of P. Yeah, so I've done two things. Multiplied both sides by epsilon naught and replaced the bound charges by the expression in terms of the polarization vector. So I do just an algebraic shuffle and I get a nice expression. So then I define D very simply by epsilon naught E plus P. This is called the displacement vector. And we get a analogous expression of Gauss's law in terms of the displacement vector. We get it to be all we have to do is know where the free charges are. In many cases, when you're talking about dielectrics, we don't know where the bound polarization charges are. It looks like a simple algebraic shuffle, but it seems like we have gotten rid of that problem. So let me do a simple example from your book. And this is problem, example 4.4. So what we have here is an infinitely long line charge, lambda, surrounded by an insulator. Of course, this extends to infinity as well. I'm just not cluttering the diagram. Okay. And this radius is some distance A. And the question is, what is the displacement vector? And what's the electric field vector if you can tell what it is? It's very often you cannot.
Is this solid or hollow?
This is solid. So it's like a wire. I mean, it's literally a wire with insulation. So there we go. Now we're able to understand what insulating material does. So yeah, this region is filled with this material. But I can easily use Gauss's law and write the displacement vector everywhere. Because the displacement vector is only concerned with the free charge. So you know from your exam that you took recently that the displacement vector is given by, or the electric field is given by what? Just tell me the electric field. If you have a line charge lambda and no insulator.
One of the two types and not R, or S, for example. S.
Okay, so I'm going to do this. But there's a lambda.
Oh, yeah.
Lambda over 2 pi S, yeah. The only thing missing is the epsilon naught. Well, that's fair because that's gone. Remember, so in D, this one. We can use Gauss's law. This relies only on Gauss's law. So immediately I can say for R greater than A, P is of course 0, and then electric field is lambda over 2 pi epsilon naught 1 over S hat. But for R less than A, I don't know what the electric field is. It'll depend on P. In fact, well, this is really no more information, but I could say for R less than A, the electric field is equal to 1 over epsilon naught D minus P.
So that first generic D that we did up there, that was for R is greater than A as well.
This is for anything, because D sees only the free charge. D does not see the dielectric.
So then why do when we define D?
Well, that's the definition of D, but when I put D here, I only get rho free charge.
Okay.
So so it sees the insulator, but its divergence only sees the free charge. So this is exactly like the electric field, except that epsilon naught doesn't appear. From Gauss's law. This is strictly from Gauss's law. Yeah? This seems a bit too easy of a problem. So let's do slightly. Problems in this category are not difficult. You just have to remember things from chapters 2 and 3. And you know what? Most of physics and mathematics is only difficult from that point of view. It really is cumulative. You can never forget algebra, right? You can't say, well, that was 5 years ago. It's done. Same thing with be it calculus or physics 1, physics 2. And it applies to your immediate past as well. When is today's lecture clear? When the early part of the semester is clear. It's not otherwise, it's all kinds of confusing because you don't have it. It's just built, everything is just built tightly. Okay, let me be specific. Let me compute problem 415. So here, the polarization vector is given to you. So you have a thick spherical shell of inner radius A and outer radius B. So let me draw the diagram first. So I have A and B. These are spheres. And only in between them you have a dielectric. over here. You have a dielectric. And P is given to you. Between walking from there to here, I forgot. K over R hat. In some sense, I don't like this K appearing because it could be mistaken for 1 over 2 pi epsilon naught. It's not that K, it's just a constant. Maybe it is meant to be that K. Okay. And the question is, find electric field everywhere. And it says use 2 different methods. One is going to be trivially easy, one is going to be slightly more contemplative. Let's do the trivially easy one. What is the trivially easy one? The question is find electric field everywhere. What is that? First of all, the displacement vector D. What component do you expect to have? This is spherically symmetric. Only the R hat component. But in this case, what is the right-hand side? Zero. Well, I can use Gauss's law all I want. I get D equals 0 everywhere. Because dr times area, 4 pi r squared, equals 0. Therefore, E equal to 0 when R is less than A and R is greater than B. But what is E equal to? D is 0, isn't it minus P over epsilon naught? Or which is minus K over R epsilon naught R hat when I just substituted this value. So problem is done. Except the question is not find the answer. The question is find the answer using 2 different methods. So obviously we have to use Gauss's law. There's nothing else we can use. And when you look at Gauss's law, you have divergence of E equals 1 over epsilon naught rho F plus rho bound. Of course, rho F is 0. From this, we will get that E equals one over 4 pi epsilon naught KQ over R squared, R hat. This is Q as a function of R. Right? Q enclosed. That is from, this comes from Gauss's law. But the problem is we have rho bound. So as a result, we're going to get possibly 2 different types of charges. You might get a sigma A and sigma B because of polarization. And you can also get a rho bound in the interior region. I shouldn't say just one space. Let's compute rho bound first so you get a sense of what we're talking about. How do I get rho bound? Well, it's minus gradient of P, which is minus gradient of K over R hat, minus, what's the expression for the divergence in spherical coordinate system? We obviously need only the R-dependent term, and I'm looking at the expression. There it is. This is 1 over R squared, 1 over R squared, dr of R squared times K over R. K over R comes from here. And there's a divided by R squared and multiplied by R squared. Yeah? And so, tell me, what do I get? The K comes out. This is just R. When I take the derivative, it goes away. So K over R squared. We found the rho bound, but now there is a sigma A and a sigma B. When I say sigma A, I mean sigma at R equals A. What is that? P dot N? Is that true, Chip? Which way is the outward normal? Minus R hat, over here.
Oh, okay.
Over here, the normal is this way. Over here, the normal is this way. And that's hence the minus sign. So what do I get? This is minus K over A. Is that true? R equals A. Sigma R equals B is K over A. Yeah? Okay. Once again, when R is less than A, Q of R equals 0, which implies the electric field is 0 because Q of R, remember the Q enclosed? That's what I mean. Now it's a function of R. Let's do when A, R, B. All we have to do is find Q. I do two things. Q is going to be minus K over A times 4 pi A squared, right? I integrated sigma. It's a constant multiplied by the area. Plus A to some R. This is my charge density. And then, R squared. This is very kind of Griffiths. R squared sine theta, d theta, d phi, dr. Is that correct? Then I have minus k. When I do the angle integral, I get 4 pi. Then when I do my r integral, what do I get? Oh, sorry, r minus a.
Okay.
Correct? So Q is basically minus 4 pi k r, or the electric field is what? Minus 1 over 4 pi epsilon naught, 4 pi k r over r squared, r hat, which is what? 4 pi's cancel. I get minus k r epsilon naught r hat. Is this the answer we got before?
Yeah.
Yeah? Okay. Now let's do
Question.
huh.
If we're integrating the volume from a to r squared.
Not r squared.
Well,
A,
sorry,
A to,
r.
yeah.
Why are we not double counting by including that sigma?
Sigma, we already did that. Oh,
Like
right.
if we start the volume, doesn't this volume start at the sigma? And
No,
then-
no, no. Sigma is an additional delta charge surface area.
Okay.
Delta
Because of-
function
Okay.
because of the polarization effect.
Got it.
There is a delta function, surface area charges, and the volume charge. Yeah. So now for r greater than a, no, sorry, for r greater than b, we know the answer E is 0. So all we have to do is actually confirm that Q is 0. So in that case, Q of R is going to be, well, this doesn't change, minus 4 pi Ka, right? From this guy. But there will be an equal but positive contribution, well, not equal, but from the sigma B. They only differ by a minus, and A is replaced by B. And then I have another from the integration, minus K times 4 pi. This time, this becomes B minus A. You see what we're doing? Replacing, going all the way to B. And indeed, what do you find? 0. And therefore, E is 0. Yeah?
Consistency to this physics.
It really just, it's a nice story. It's a tight plot. It's like the first 2 seasons of Game of Thrones. And again, every time I go through Griffiths, I can't help but admire the way he's written the book. He says, a deceptive parallel. So, look at this. You have divergence of E equals rho over epsilon naught, and curl of E equals 0. And as a result, we have this expression. So it implies 1 over 4 pi epsilon naught rho of r prime. This is just to recall. And correct? But we have divergence of D equals rho free. Correct? So you may be tempted to write this as, first of all, the epsilon would disappear, epsilon naught, because there's no epsilon naught. You might be tempted to write this as rho free but he gives it away by saying it's a deception. So but we cannot do this. The reason being, curl. This requires that the curl be 0, because this can be written as the gradient of something. Gradient of the curl is always 0. What is it? Isn't gradient of 1 over r minus, yeah? This is the gradient. So I can pull that gradient out. So curl, right? So let me do that. Minus 1 over 4 pi epsilon naught gradient rho of r prime over r. So the electric field is the gradient of something. Therefore, the curl of the electric field is 0. But that's a check. In this case, curl of D, well, it's going to be curl of epsilon naught E plus P. Well, curl of E is 0, so this is curl of P. Yeah? Indeed, if you have a region where the curl of P is smooth and is 0, we can write, so in a dielectric material, when curl of P is equal to 0, then D minus 4 pi rho free yeah, but this is tightly connected to this requirement. There may be some polarization where the curl is 0. In particular, if polarization is a uniform polarization. Then we have an easy expression. Otherwise, we don't. Okay. And then let me talk a little bit about boundary conditions. Implies what? See, suppose you have some sigma. This implies that the perpendicular component of the electric field above So in that case, this comes from only this. Yeah. So that means we can draw this parallel, d perp above minus d perp below equals sigma free. Yeah? Now the parallel components, curl of E equal to 0 implies E parallel above minus E parallel below is equal to 0. But curl of D is equal to curl of P. Correct? It's curl of epsilon naught E plus curl of P, but E is curl free, so we get curl over curl of E minus P equal to 0, which tells you that D parallel above minus D parallel below is equal to P parallel above. We have no further information. The rest depends on the nature of the polarization vector field. We cannot guess anything. Good. Now comes a class of objects that are very important. They're easy to handle with. That's why they're important. We give importance to things we can do. For Martin, running a marathon is important. For me, no, not so much. I can't do it. Linear dielectric material. We talked about some of this. A large class of materials. There's no polarization. Yeah? There's no net polarization. But you turn on the electric field. Then what happens? You get this dipole formation, right? You will have positive charges and negative charges scrambling to their respective ends. Martin, how many miles can you run in one day?
I'm not a marathon.
Right. If you train for that, you could do much more.
Right.
7 miles is, I can drive that pretty well. Good. So, you turn on the electric field, you're getting a polarization. You crank up the electric field, you get a little more polarization. You dial it down, a little less, until the whole thing breaks down. So when I say linear dielectric, there is a range of electric field where the response is linear. But that's a very important range. And in that range, the polarization vector is proportional to the electric field. So many materials are linear about a certain value. But that is a good range because on the average, there's no electric field here. So you get to dial it up and dial it down. Now, with this in mind, what we're trying to do is, this is just not important here, but just to motivate my definition here, you see there's an epsilon already here. And this is P. It'll be good if I can put an epsilon naught here too. So with that in mind, I'm going to just put an epsilon. Because I get to play with the constants. I can call it whatever I want. And the remaining number, so that this works out right, is picked to be chi E, chi sub E. And such material, so it's a constant that you have to look it up. Chi sub E is called the electric susceptibility. Yeah, it is. Does that look right? When this is true, for the materials this is true, we say that it is a linear dielectric. It makes life very simple. In this case, oh, this actually became handy. Yeah? Because P has been replaced by E. Now I can call this, and I want to box it, so I'm going to write D again. I'm just going to call this epsilon, no longer epsilon naught. What's the word for epsilon naught? What did we call it? Permittivity of free space. So what is epsilon going to be? Right, permittivity of the linear dielectric. It is the permittivity linear dielectric.
For free space, chi would be 0.
For free space, chi would be 0. Yeah. Now, there's another thing that is often used. I don't. This is, of course, 1 plus chi E. But this is called the dielectric constant. Too many definitions. This is what I use. Okay. So, let me get started on example 4.5. If I can finish that, that would be great. Notice that there's a circle. What is a circle? It's a metal. And on a metal sphere of radius A, charge Q is placed. So where do you think the charge is going to run to? To the surface. And then it is surrounded by a linear dielectric. Of permittivity epsilon. So there it is, by definition, by the nature of the problem, there's already a sigma free here. The charge Q what is sigma free? Q over 4 pi a squared. And I think it wants a few things. We may or may not be able to complete this problem, but okay, it says find the potential at the center. So to find the potential at the center, we have to find the electric field so that we can integrate the electric field. Yeah? I already know one thing. And R is less than A, D equal to 0 equal to. There's no polarization, there's no electric field. But now, this is a linear dielectric. So there's going to be an electric field. Oh, I can even do it. I don't care. And R greater than A. Tell me what D is. 1 over 4 pi. There's no epsilon for D. Yeah? Total charge enclosed over R squared, R hat. This is a linear dielectric material, which means E equal to 1 over 4 pi, watch this, epsilon Q over R squared, R hat, when E breaks into two values. Yeah? So I have given you E in all three regions. The question is, what is the potential at the origin? Well, start from infinity to 0. Correct? I will let you finish this. I want to talk about a few other things. But I'll say one more thing from here. So I'll have E minus infinity to B 1 over 4 pi epsilon naught Q over R squared R hat dot DL, or I can do dr minus B to A That's where the r hat dot r hat is just 1. And in the inside region, it is 0. So basically, it just comes to an integral of 1 over r squared. So you can do the integral, but let me write it down for completeness. Please verify that this is q over 4 pi comes out. It's a very believable result as well. Yeah? But what I want to mention is the following. There's electric field in the inside region. And because it's a linear electric field, there's a polarization vector in the inside region. Because there's you can expect the polarization vector, like the electric field, is going to be radial. Therefore, there is going to be what? A sigma bound. Sigma bound. Oh, no. It's not good. Yeah? This will be a negative charge. This will be a positive charge. So the inside over here, the electric field is going to be slightly less. Because why? The net charge inside is slightly less. Epsilon is bigger than epsilon naught. So the electric field has been diminished. So in this sense, an insulator is like an imperfect conductor. A conductor would do what? Bring the electric field down to 0. A linear dielectric does what? Weakens the electric field. Is that clear? I mean, the fact that it weakens, you can just see by looking at this versus this. This is bigger than that. So the dielectric diminishes the electric field. All of you are very patient as I constantly overstay my welcome.